So here we have section 8.3, and this is all the dot product stuff in more detail than was in 8.1. So again, we know what a dot product is, and let's remember our properties. Okay, so we'll just remind ourselves of these. So one, distributive property over addition. So if I have x dot the sum y plus z, I can write that as x dot y plus x dot z. Two, it's commutative, so x dot y is y dot x. Three, a scalar can be moved around, so I've got tx dotted with y. I can write that either as t times x dot y, like that, or I could move the t to the y and have x dot ty. 4. Now I prefer to get rid of Roman numerals, but hey, they're using them, so I'll stick with it. And we have x dot y, x dot x is just, now they write it as a squared plus b squared plus c squared if x equals abc, but I'm going to write it as saying that this is the norm of x squared. 5, x dot y is the same thing. If we think of everything as column vectors, this is the same thing as x transpose times y, which means that's also the same thing as y transpose times x. And so we can write those either way because they're a real number. And 6, the dot product, since we've got that it's the square of the norm, then this equals 0 if and only if x equals 0. 0 vector there in that case. Okay, so again, they mention the writing vectors. They say writing vectors, say a vector ABC. We can write that as the linear combination of our standard unit vectors, c times k, like that. And let's see, they mention they talk a little bit about unit vectors and so forth, so we'll toss those in. If I have a multiple inside of the norm, I can factor that out as an absolute value times the norm of x, and x over its norm. Now they mention plus or minus, so sure, I'll put a plus or minus, is a unit vector. As long as x is not equal to the 0 vector. And we've already done this in our section 1, but they do point out again that x plus or minus y, the norm of that, can be written as the norm of x squared plus or minus 2 times x dot y, and then plus y, norm of y squared. Okay, and we already saw that. All you do is you take either x plus y or x minus y and dot it with itself, and there you have it. Okay, and so then they go through. They mention the theorem 8.3.1 is Cauchy-Schwarz. Okay, and again, the Cauchy-Schwarz is that the absolute value of x dot y is less than or equal to the norm of x times the norm of y. And again, because of this, the Cauchy-Schwarz and this, that's how we get the triangle inequality. So when I'll mention the triangle inequality again, but I won't do the proof. We already did that where we use the Cauchy-Schwarz right there to get our inequality. So Cauchy-Schwarz, this is an interesting, I like the way they do this. So their proof of Cauchy-Schwarz is they'll take, well, first they point out that if this is the zero vector, then it's trivial, okay, because we just get 0 is less than or equal to 0. So if x is not equal to 0, then we'll take some real number t, and let's look at 0 is less than t x minus y, like this. Okay, now go ahead and square this. So this is equal to tx squared, and then minus 2tx dotted with y. And I could put some parentheses on that in places, but again, it doesn't really matter where I decide the t is sitting. And then the norm of y squared. And so again, we just do the dot product and get that. Now we factor out our t, and we get t squared x squared minus, and now they do 2x dot y like that, all times t, and then plus y squared, magnitude there. And so they say, look, we've got a t squared minus 2bt plus c. Okay, so they have that quadratic. And okay, and they know it's greater than or equal to 0. And a is not 0. Okay, a is not equal to 0 since the norm of x squared has to be greater than 0 because the norm of x was, or because x was not 0. And so now they factor out an a, and I think they divide by it at some point, but so they wrote that they have at squared minus 2bt plus c is greater than or equal to 0, but that means that t squared minus 2b over at plus c over a is greater than or equal to 0. And then they just complete the square, is what all they're doing in their next step. So they say t minus b over a quantity squared plus ca minus b squared over a squared is greater than or equal to 0. And again, all they did was complete the square. When they take this part and they toss in a plus b squared over a squared, they had to subtract that out, and they got a common denominator with the c over a by making that ca over a squared. And so again, all they're doing there is completing the square. And then they say, well, let's let t equal b over a. Okay, which is perfectly fine. So we tossed in some constant. So, think about that. We tossed in some constant t, well, way back here. Okay, we never said what that constant t was. And so now let's say that it's b over a. Well, in that case, then that leaves ca minus b squared over a squared has to be greater than or equal to 0, no matter what a, b, and c are. And so if this is greater than 0, the denominator's not negative. And so since it's positive, that implies c minus b squared has to be greater than or equal to 0, which means that b squared is less than or equal to ca. And if I take the square root, that says the absolute value of b is less than or equal to the square root of ac, which we could write as the square root of a square root of c. And there we have it, because remember b, looking back here, b was that dot product. So we end up with x dot y is less than or equal to the absolute value of that dot product. And then a was the norm of x squared, so this is the norm of x. And c was the norm of y squared, so that's the norm of y. And there we go. There is our theorem 8.3. Okay. And, they mentioned, then they look at, well, okay, we've got less than or equal to. I can't seem to move this all of a sudden. Let me kind of do that. There we go. Huh. I don't know. So, what about x dot y equals x y, like that. So under what cases? Well, again, remember that we thought of this as cosine theta. So another way to look at this, now they're doing it slightly differently, but what we have is, remember that we said, oh, cosine theta was equal to, oops, x dot y over the norm of x, norm of y. And if we want equality, then we want this to be 1 or oops, again, I put some absolute values there for cosine, which I didn't want. And so you see, we want this to be plus or minus 1 in order for equality up here. And, you know, but if that's plus or minus 1, then theta was 0 or pi. And so we get equality exactly when, you know, x is a multiple of y or vice versa. And so that is the case for equality. Then they mention the triangle inequalities. And we already have proved that, and you know, so you know, we just have our triangle inequality that x plus y is less than or equal to the norm of x plus the norm of y here. Okay, so there's our triangle inequality. So those are two biggies, Cauchy-Schwarz and the triangle inequality. And there we go. That is 8.3.